Okay, so we are going to get started on the second part, if you would, of Module 6, and that is going to be looking at threads and fasteners. This is the PowerPoint presentation that goes along with Chapter 13 out of your tech drawing book. So it's the big thick one, okay? So I am going to click on that PowerPoint presentation, and that is what we're going to use to kind of guide us through that chapter. Now, I'm not going to read these objectives to you, but pretty much what we're going to be doing is we're going to be looking at threaded fasteners and how to call them out on drawings that pertain to things that we're going to see in mechanical design. Okay. So as we look here, first of all, threaded fasteners and threads are going to be used for three basic applications. The first application, which is probably the majority of the things that we see it for, is to hold parts together. So when we have multiple parts that are going to be assembled, we want to make sure that we secure them and that they're going to stay together. And we do that with fasteners, okay? They also can provide adjustment on different things. So you can see here in this middle photo, there's an adjusting screw there, and it looks like it's a drum to me. So it's to kind of hold that the top in place, but then you can also tighten it down as needed, okay? And then the third way you're gonna see here, this is a jack, and this is going to be using a threaded fastener, a nice long one, but this is going to be able to transmit some power in order to lift something or hold something up, okay? Now, as we look at threads, this page is not correct. It says study page. This was from a previous version of the book. When I looked in the book, I believe it's page 595. So this page right here should be 595 in your textbook. And there is a nice comprehensive list of all the different vocabulary or words that are going to be associated with the things that we're going to be talking about here, screw threads. So when we think of screw threads, we call them threads. And what is happening is we have a spiral effect of these peaks and valleys that go along a feature. Now, threads can be internal, meaning that they are threaded or tapped into a part. We call it tapping. Or they can be external. So they can be on the outside of, most often, a fastener for sure. But then we can also cut threads into round stock, like on a lathe. So you can maybe put it in sections on maybe a shaft or something like that. Okay. Now, as we look here, when we talk about nomenclature, that's just a fancy word for vocabulary, okay? And when we look, this is a really nice view of what a thread looks like, okay? So first of all, the couple things that are probably the most important are going to be the major diameter for one, okay? Major diameter, as you look here, it's dimension 2, the very top of what we call the crest of the tooth, okay? And you can see that pointed to right here. So the top of the crest of the tooth is the very highest point, if you would, on the thread. Now, the major diameter, if we would take a calipers or micrometers and measure across that major diameter will always be what we call the nominal size of that thread. So for instance, if I have let me grab this one out. If I have a fastener, okay, like I do here, this is a socket head cap screw. I know for those who are virtual, it's probably not as easy to see, okay? But if I would take and I would measure from one side of the thread to the other, okay, that is going to be what we call the nominal dimension. So when we call out threads, especially if they're English threads, well, the metric as well, they are going to have a designated size. And in the like English standard, they're going to be two common fractional divisions. So for instance, a 1/4 socket head cap screw, that 1/4 inch is its nominal size. That means when I would measure the top to the bottom here on the major diameter across those crests, that is going to be equal to 1/4 inch. If it was a 5/16 -13, okay, then it's going to be 5/16 across. Or if it's a 1/2 inch nominal size, always going to be, that's going to be over the major diameter. So they're really easy to determine what the size is just by measuring the outside over the major diameter. The next diameter, I'm going to go in a little bit here. This is called the minor diameter. And as you can see, where it's dimensioned to is going to be to what we call the root of the tooth. It's like the smallest diameter in there. It's the bottom of the thread, okay? So that is going to be the minor diameter. And then in between here, there is not a definitive like measurable place, but it's called the pitch diameter. And you'll notice that it is dimensioning to like a little center line. It is not in the perfect middle of the tooth, but it is the place what we call the effective diameter, meaning when we tighten this up, that is where all of the strength of the threads, whether it's on the fastener and or inside on the internal threads, is actually being transmitted and where it occurs, okay? So the pitch diameter is really important, okay? The next thing that you're going to see here is thread angle. Different types of thread profiles are going to have different angles here, okay? And even the tooth can look, or the thread can look a little bit different. The next one is going to be pitch, okay? Pitch is going to be what is the distance from one point on a thread to the very same point on the next thread, okay? And that's going to be the distance really apart of each one of those threads, okay? Some are going to be closer together, some are going to be further apart. Now, as we look at an internal thread, you're going to notice those very same things that we're talking about. The root of the thread is at the bottom here. The crest is going to be at the top, but these are now cut internal to the material, okay? Internal to the material. Something about threads, I just want to make sure I get it in here. When we want to thread together, okay, or have these mate with one another, we have to have the same size thread call out both internally and externally, okay? Otherwise, we can't thread them together. So for instance, I can't put a 5/16-13 into a 1/4-20 hole, okay? And maybe that's, you know, I mean, it maybe makes a lot of sense, but it's worth saying you have to have, when you design whatever the external thread or the fastener that you're using, that is what you have to tap your holes to, okay? So it's important to match those up. All right. Now, these are different types of thread forms, okay? And there are a ton. There are really a ton. And the two in mechanical design that we are going to come across that are the most common are going to be the unified, which is down here. This is C on our illustration. So unified right here is going to be the one that we use in mechanical design and are the standard threads for the fasteners that we're going to be designing for. And the other one is going to be metric, okay? And when we have metric, threads and parts that we're going to be designing, those are going to be the ones that we use. The other ones that we see here are going to be for some other specialized applications, okay? I can't speak to every single one, but the ones that I know are Acme threads, okay? Acme threads are going to be used a lot when we have things like lead screws and we need to push a lot of force and power through those, okay? Buntress is very similar. We see these a lot on machine tools. Again, they're going to be more that heavier duty application. The buntress is nice because it doesn't allow for what we call backlash. That's why there's a vertical on that backside of the thread. And then squares are also going to be a very, very common one for applications, just like we talk about with the Acme. Again, more power through them. If you'll notice, there's just a bigger, chunkier top to it. We don't get the peak on it, so they're going to be less likely to strip off or shear off, okay? So the other ones, again, more specialized for different applications that I quite honestly aren't really familiar with. The three that I've used out in industry are going to be unified, metric, and the Acme threads, okay? So thread pitch. Now, we talked about what the threads look like, okay? And they're basically spiral V's that go around the outside or internally on an internal hole. And as we look here, when we talk about thread pitch, there are two ways that we call it out. There's the English way, and then there's the metric way. The English way, I'm going to zoom in here, okay? What we do is we count how many threads per inch there are, okay? How many threads per inch? So if we look, we measure out 1 inch and we count first pitch, second pitch, third pitch, fourth pitch. How many pitches did we get in there, okay? So there will be 4 in 1 inch, okay? If we look over here, you're going to see that we see, and they have the number down below, if we count how many peaks we have here, there's 8 pitches or 8 threads that we can get within 1 inch. Now, as you can imagine, as we can physically see, 4 to 8, as this number gets larger, the threads get closer together because we're getting more within an inch, okay? The English way to call out thread callouts is per inch. So, for instance, when I have a 1/4-20, okay? So I'm going to put that underneath my thing here. So if I have a 1/4-20, okay? The 20 is that threads per inch. So that means that the outside diameter of my fastener is 1/4 of an inch. And if I would measure an inch long, I would count 20 threads in 1 inch. That's what that designation means, okay? There's also another variation. It's called a 1/4-28, okay? Same thing. Those are going to be the threads per inch. So what happens is when I measure that inch, I'm going to get 8 more threads for that very same size, okay? 8 more threads. So, so whenever we call out on drawings, we have to call out not only the nominal size, but what are the threads per inch? And that's the number after the dash, okay? Now, metric threads. Metric calls them out a little bit differently. We know it's a metric thread when we see an M in front of it, okay? The English is, now I did it as a fraction because it's actually acceptable to show it in both ways. You can either show it as 1/4 or you can show it as 0.25-20. Both are acceptable in the standard. I do 1/4 because I always say 1/4, so I always call it out as a fraction, but either way is acceptable. Neither one has been deemed the old way yet. Okay. But metric, theirs is always an M in front of it. So you know right away that you're dealing with a metric thread. Okay. But the way that they call out their pitch is a little bit different. Instead of a dash, they show a by. Okay. So they have an X. So it's an M8 by, and in this case, 1.5. Well, it's not 1.5 threads per inch on an M10. So an M10 is going to be 10 millimeters across the major diameter. But now what they're doing is they're measuring from one point on a thread to the very next point on the thread. What is the dimension between the threads? So it's not threads per inch, it's how far those threads are apart. And so an M10 by 1.5 is the pitch is 1.5 between each one of those peaks, if you would, of the threads, if you're measuring the peaks. Does that make sense to everybody? So a little bit different way that they call it out, a little bit different way. Now, these are a couple different other kinds of threads. Again, I'm just focusing on what we're going to see most often. So those are the ones that we see at the top here. Now, thread series. We have 2 main thread series, but there is a third that you don't see very often. The 2 in mechanical design that we are going to be seeing are the coarse and the fine. Okay, coarse and fine. Now, because we are using the unified national thread type of thread. So if we go back up here, remember when we said that we're a unified, that's the one that we see on our fasteners. That's what the U in the UNC means, okay? Or the UNF. So these 2 right here, these are the only 2 that we're going to worry about. Unified national coarse thread. Okay, coarse. So coarse is going to be a classification of how many threads per inch you have. Okay, so as I stated earlier when I was underneath here, there are 2 sizes, if you would, or 2 threads for a 1/4 inch fastener. So if this is a 1/4 inch fastener, one of them is 20. This is the UNC call out. This is the coarse call out. Okay, if I call it a 28, that's a UNF call out, the fine thread. Okay, so coarse, it's kind of like the run of the mill, the basic one. Fine is going to be, that's when we get those extra threads in there. Okay, so UNF or UNC. Only 2. We're not going to talk about any of these other ones. I'll talk about one other one. Extra fine. Okay, the next one over is extra fine. I've never used it when I was out in industry and I was specifying threads. I'm not saying that it's not out there, but this is going to be for very fine adjustments on things like watches and clocks, maybe those tiny little screws that you have in your eyeglasses, those types of things. That's where we're going to see fine threads, but that's not in the industry that we're in typically. So I'm not saying you're never going to see it, but there is that third class, but again, not used very often at all. Okay. Right hand and left hand threads. Right hand threads are going to be it's going to be the assumed, okay, the unsaid one, if you would. So when we're calling out threads on a drawing, if we don't put LF in back of it, that just means we're automatically right-handed. And right-handed is the typical righty-tighty, lefty-loosey. So we're going to tighten up going the right hand way or going clockwise, and we're going to loosen it up going the left hand way or counterclockwise, okay? If we need to use what we call a left-handed thread, then we have to call that out on the thread. So for instance, if I go back underneath my camera here, and I would say a quarter 20 UNC, and then dash, I would see an LF in back of it. That means that I tighten left hand or counterclockwise as opposed to. Now, when would we use that situation? Typically on things that are spinning, okay? So if the direction of spin is in the same direction that you could possibly loosen something up, you want to change that direction, okay? And that's usually when you do it. So, and that's not used all that often, but in the event that you need a left-handed thread, we got to call it out. If it's always right-handed, it's assumed. That's going to be the standard direction, okay? Single and multiple threads. And all this does is this just applies to what we call the lead of a screw. So if we are using screws for the purpose of adjustment, okay, then what we need to know is how many turns does it take to go a certain distance. Now that is going to equate to what your pitch is. So for instance, if I have a standard pitch, they call it a one start. When I rotate around one time, I'm going to move the distance of one pitch. Okay. If I go around two times, I'm going to move two pitches and so on. Okay. There are threads out there. Again, they're not going to be the ones that we deal with. Okay. But basically what they're saying is when you go around one time, you might be getting a further distance along. Okay. So you can go around multiple times. Okay. Not the threads that we deal with, So those are special applications. American National Thread fits and metric unified thread fits. So there are three classes of fits, okay? And this is for the English or the ANSI standard, the American standard. Class 1, Class 2, Class 3. Class 1, these are going to be low grade fitting screws, probably things that you would maybe use. I don't even know if you'd use them there, maybe on toys or something like that, okay? The class 2 is going to be like the standard one that we use for industrial purposes. And that is going to be anything like with a socket head cap screw or the screws that we use, in industry for the things that we deal with. Okay. Class 3 then is going to be one level higher than that. Okay. Class 2, if I put a nut and on a bolt, for instance, I'm going to feel just a little bit of difference in there, but not very much. Okay. There is a little bit of gap because I have to freely get the thread, on and off. Okay. Class 3, I'm going to feel almost nothing. Okay. It's going to just be really super accurate, not only the internal, but to the external thread. Class 1, not good at all. Okay. You can really feel a lot more gap. So it's all about kind of how close the fit is between the external and the internal threads when I actually thread them together. Class 2, these are going to be the fasteners that, number one, I use industrially, and they're going to be the ones that you get at the hardware store. Okay. I don't know where you get class 1, and then class 3s are going to be special order, if you would. Okay. So, class 2s is what we'll be specifying. Now, in the designation, well, I think that's coming. Okay. We'll get there. Okay. We won't worry about that. In metric, there are two general classes. There's 6H and 6G, okay? And they don't really call them out as whether they're, different grades. They just call out internal or external, okay? So they don't really have different grades for their fasteners. They're just one grade, and the 6H is for internal and the 6G is for external, for instance. Okay. Showing threads on a drawing. There are 3 different ways that we can show it on a drawing. There's the detailed, the schematic, and the simplified. The only way you're going to show them is simplified. You will never see the other 2 on drawings at all. And I want to show you them, but the only way we're going to specify them, and this is the ANSI standard, is in simplified form. So the detailed, this is where we show each one of the threads, okay? The only time we will ever model or draw threads is when we need to manufacture them. And really the only reason we would manufacture them in our case would be if we'd want to 3D print them on our 3D printer, okay? In that case, we would have to model the threads and show them as we see here. But we wouldn't even put that on a drawing, quite honestly. We would draw them still we would show them on a drawing in their simplified form. But modeling wise, we would model the threads. As we look at schematic, schematic is if you would, a more simplified version of, okay? And you're going to kind of see here that they have these lines, okay? It's just a simplified method of doing it, all right? What has been adopted by the ANSI standard is the simplified version. And that's where we show it. I don't even really like this version that well. I'm gonna go down here. This is going to be a simplified version. This is on slide 12 if you're following along with me. And all we see is we see the drill. We'll talk about tap drills in just a little bit, but then you're going to see this hidden line on the outside of this. This is reflecting where the threads would be. So there's really kind of like 2 diameters when we see it actually internally. There's going to be the root diameter, and then there's going to be the thread, you know, the crest or the major diameter, and that is into the material. So we show that as 2, if you would, diameters at 2 different distances. Okay, so simplified only. Thread notes. So how do we show it on an actual drawing? Now, there are 2 schools of thought, and it really it's going to depend on your employer, okay? Where I worked, we all understood we wanted to keep the drawings as simple as possible, and we wanted to also let our machinists make some decisions and based on their knowledge and experience. So when I'm going to have you call them out on drawings, I'm going to do it the way that I'm used to, and I think it's a cleaner way of doing it, is we are not going to call out the tap drill size that we see on top here, okay? When we tap a hole, and that means internally, when I tap a hole, I'm going to go underneath here for a second. It takes 2 operations, okay? 2 operations. So if I look at my block, I've got a threaded hole right here. So how this occurs is we have to have a through hole first, okay? So I am going to drill out however deep my threaded hole is going to be. In this case, it looks like it went all the way through, okay? And that drill size is going to be equal to the root diameter or the minor diameter of our thread. So we're taking out all the material like that's on the inside first, okay? Then the second part of the operation is I am going to use a tap, okay? The tap has the little threads on it, there's peaks and valleys there, okay? And then once that goes in, that doesn't take out, I have to do the drilling first because that takes out the middle, if you would. And then this is just going to rotate and it's going to put the threads in place, okay? Going to put the threads in place. So 2-part operation. So when we look at the call out that they're using here, that top line is my drill size, my tap, they call it a tap drill size, okay? Now, for those who are in class, okay, you got a freebie today. 2 things. Where you're sitting, you're going to notice that there are 2 charts that you have here. One is just a decimal equivalent from metric to English, but the other one is a tap drill sizes, okay? Tap drill sizes. So, for instance, zoom. What I want to do is I want to find what is, and I know it's going to be hard to see on here, what is the tap size that I have, okay? And I'm going to go down to the 1/4 20 for right now, okay? And what I'm going to do is you'll notice that I have a quarter, 20. Now a quarter is 0.25, right? Quarter is 0.25. So what I'm going to do is I want to line up what is the drill size that goes along with that. And in this case, if I go over to the left, the equivalent trap drill size is going to be 0.2. Okay, 0.2, which is a number 7 drill. 0.2 is 50 thousandths less than 0.25, right? So they're drilling out with the drill first, 0.2, and then they're coming in with the tap, and on the major diameter that is created, that is going to just take out 50 thousandths, okay? And then in the form of the actual threads themselves. Does that make sense to everybody? So if you're unsure of what the tap drill size is, now these are standard. So once I know what the size thread I need to create is, the person who is making the threads is going to have a chart like this. Okay, it's standard. Or they might even just know what it is if it's a common thread that they make on a regular basis. So when we call that out, it is acceptable to leave the top off, because this is the tap drill that goes along with the 3/4 by 10. Okay, so in this case, this is a 3/4 inch diameter fastener, 10 threads per inch. Okay, they have NC. That means it's the National Form Coarse thread, because that's a -10 is a coarse thread, and then a -2B. The 2B is already assumed. Number one, the 2 means it's the class of not the class of fit. Is that what they call it? Did they call it the class of fit? You might have. Maybe that's right. Oh yeah, it's thread fits. So it's the class of fit. And then B is just a designation that this is an internal thread. Well, I can see it's an internal thread, right? And it's not going to be anything but a 2. We're only going to call it out something different if it's not 2. So you don't need the 2B on there. You do need, if you are doing a left-hand thread, you would need the LF directly in back of it. And then this is the full call out with, again, if we are not a left-handed thread, we don't need to put the 2B on here. We can stop right here after the C. Okay, done. And then we can say how deep we want that thread to be. In this case, they want it to be a depth of 1 inch. All right. So you don't need to do the top. You just need to call out the thread, because we're going to assume that your machinist who's putting this in, or anybody, has the standard tap drill sizes, available to them. Now, this is how we called them out, not only in industry, but it's an acceptable way per the ANSI standard, because we like to kind of simplify things on a drawing, if you would. The more that you have on there, the more you have to read and things like that, more to interpret. So your company might be like, nope, we want the drill sizes on there, so you have to add those. All right, so you will do it however your company does. So I'm not saying it's the only way to do it, but you might see variations on this. And that top line will be the tap drill first, and then the bottom line will be the thread call out that is required. Okay. The M's here, they do not, or the metric, they do not call out drill sizes. They just don't. That's not part of their designation. So you wouldn't have to do it with that. That's just going to be like an M10. That J or H or in between is going to be their fit, but most often you just see it as an M10 by 1.5. Okay. And Acme, again, is not going to be something that we're going to see very often at all. Okay. Oh, something I do want to point out. So when we call out our thread designation and we give the depth, that's the depth of the thread. That's how far down our tap drill is going to be, or our tap is going to go. That's going to go down to, you can see about here. Our drill will always be further, always, okay? Always be further. By how much? Again, we give discretion to the person manufacturing it. Most often it's going to be dependent on the size. It's usually going to be half of what that diameter is. So if it's a 1/4 20 socket head, or if it's a 1/4 20 UNC, it's going to go an additional 1/8 of an inch. You can see here that this is a 3/4 inch nominal size thread. It went 3/8 of an inch further than the depth of the thread. So half of whatever the diameter is. or something else. I mean, if somebody, at least that you want to go. And the reason for that is because there's going to be threads that are going to come out on this tap. They're going to be smaller, but there's going to be threads and they have to have a place to go. And that drill, there's a tip to that tap. So we have to make sure that it can go down as far as it needs to, if you would. There's a little top to that. Okay. So the drill goes down a little bit further. Okay. And then the tap is going to go in not quite that same distance. Does that make sense? Okay. All right. So you have a little bit of freedom here, but again, you want to do whatever, you know, the company that you're working for does it. So you might see the variation where they do want you to put the tap drill in there, and that's okay. No problem at all. But for me, we're just going to stick with the designation of the thread. Simplified schematic threads. Yep, we don't need to look at this. Internal symbols. So here, how we're going to be showing threads, simplified version. So anything on this top line is what we would see. So for instance, when we see it in a circular view, we're going to see it as 2 circles. The internal circle is going to be equal to the size of the tap drill. The outside circle is going to be the size of the nominal size of your thread. So if we're in this case, well, this is an M20. So this is going to be 20 on the outside, and whatever the corresponding, usually about a millimeter and a half, going to be smaller as far as the tap drill for metric. But if we're in the metric, we're going to take the tap drill size. So we had just looked at a 1/4 that was a number 7 drill at 0.2 diameter. That's going to be the size of the inside circle, because that's equal to the root diameter. And then the circle that's on the outside that is in a hidden line format is going to be equal to the 1/4 inch, or the nominal size. Does that make sense to everybody? Why do you think we show this outside circle as hidden? Any idea? Why do we think? So if I look straight down here, these guys are on the inside, right? They're in the material. It represents the tip of these, that when we look at the top, if I would tip this up, I wouldn't see those, right? So that is the top of the internal threads equal to the major diameter. Okay. Now, when we show them in the part, now if I have a through, so if I'm tapping through, I'm just going to show the two lines representing the inside and that outside diameter, if you would. Okay. If I section it, the inside diameter is going to be shown. The hatching will go up to that inside diameter, and then it would be a hidden line. This is the only hidden line you should be showing in a section view. That would be for a thread. Okay. On the outside there. If you have it to a depth, okay, this is called a blind hole. A blind hole is when we are to a depth and we're not going through. So here you're going to notice that we have the end of the drill here. The flat on the drill is going to be the depth of that tap drill. Okay, so again, about an additional half, whatever the diameter is here, whatever that length is. And then we're going to show the depth of the thread based on the call out, like here. So this would be equal to the 1 inch in this case. Okay. So blind, and then this is considered through. If I'm sectioning, we can kind of see that difference there as well. We typically don't do this. You always show a tap drill that's a little bit further. So I've never done anything like that. And then if we're showing it on the back side, looking through, then we would show the inside hole as hidden. So if we're looking through material and we know that there's a tapped hole there, we would show it then both circles hidden. So yes, Chris.
Like a drill to a depth, is there a specific angle for the peak of the drill?
Yes, it is 82 degrees inclined or included angle. So this would be 82 degrees or 41 and 41. Yeah, that's typically the angle on the end of a drill. Good question. So the question was, what is the angle on the tip of the drill here? So most often it's 82 degrees included unless otherwise specified. So it would be 41 degrees in either direction from horizontal in this case. Okay, thank you. All right, any other questions? So good. Tapped holes, just kind of talked about this. This is talking about the tap drill. They have a little bit different here. So they have a 30-degree angle. They're all a little bit different. Most the one I'm always used to is the 82. So it's 41 and 41. But here's that tap drill is going in first, then the depth of the thread, and we've shown, you know, that process and how we should represent that. Bolts, studs, and screws. Okay, so these are going to be the elements that are going to be holding our items together. So these are the actual fasteners that are going to be going through things and securing them. So we have a couple different ways that we can call things out, or a couple different fasteners that we can use. A bolt. A bolt is going to go through, for instance, a couple of what we call clearance holes. None of them are tapped or anything or threaded. And then that bolt is going to be long enough so that on the back side, if you would, we can secure it with a nut. So this situation, but holding a couple things together. Okay. The next one that we see here is going to be the use of a cap screw. A cap screw, its purpose is to thread into a threaded, in this case, it looks like a block or a, you know, a plate or something like that, where it would be a clearance hole on the top. So it would go through a clearance hole, no threads. Clearance hole just means that there's no threads. It's a little bit larger than the diameter of the fastener that we're going through, and it's gonna go right through, but it's going to thread into the next element. Okay, so that's the purpose of the cap screw. Cap screw we would not use. That would go through and actually secure on the backside with a nut. Typically, that's going to be the purpose of a bolt. Okay. And the third one that you have here is a stud. And in this case, this is going to be a threaded stud is going to have threads that are going to be going into the second element, similar to a cap screw. But on the top here, there's going to be a portion of it that is not going to be threaded. So that's really the only difference. Now, there are different heads on screws, okay? And you can see them all here. Now, you are not going to see either one of these types of heads as far as tightening down. You will not use slotted screws out in industry. You will also not use Phillips screws out in industry. You will use most often socket head cap screws and hex heads, okay? That's it. And there's a really good reason why, especially if you're working with guarding and you are OSHA regulated, okay? So, and the heads are okay. It's just the means of tightening that's the problem here, okay? So let me show you a couple instances here and I'll explain why, okay? You will find slotted screws, Phillips screws in the toolboxes, for instance, for CAD programs like SolidWorks, okay? But you won't be using them, okay? So the one that the kind that we have here are socket head cap screws. In the top, there is a hexagon, okay, that goes down in here. Most often, Allen wrench, that's actually a name brand. So it's not officially called an Allen wrench, an Allen screw on the inside. It's a slotted hex screw. So then you're supposed to use a hex key to actually unscrew it, but it's an Allen wrench. That's what we all refer to it as. Now, the reason we use these out in industry, especially when we're talking about guarding and OSHA regulations, is that you need an actual tool to undo these fasteners. Okay, they also will torque down better for you as well, and the heads won't deform as easily. Okay, they're hardened heads. Now, if you use a slotted screw like we see here, sure, you can get a screwdriver to take it off, but you can also get a coin out of your pocket to take it off. You can get a butter knife to take it off. And if you use these screws out in industry, just so you know, and I know this because we dealt with automation equipment. We would put, you know, guards on things, and we had to use these. We had to use the socketed cap screws, because if guards are taken off and they have any slotted type of a screw head on them, the company is liable who designed that guarding. Okay. even though somebody to me is gonna, if they have to physically go get a tool, then it's on them, the individual who took the guard off. Does that make sense? But if they can just pull something out of their pocket, now the company is liable. Does that make sense to everybody? I'm not here to be a legal person, but I dealt with that kind of stuff. And it seemed kind of silly at first, but then when you start looking at slotted screws, even at home, a couple times you torque on them, they're all messed up. Okay. And we want these to be able to, either take off or put on and hold the integrity of tightening and loosening them up. Ava, yes.
Government projects that a company is running should have a guard, like a guard on it, correct?
I can't speak for that. I don't know. If there is the chance, it is always good practice to put guards on things. If there is a chance that somebody could get hurt, if they would, encroach on the area wherever, work was being done by a machine. I can't say that, oh, if it's a government project, it should be guarded. I guess it just depends on what's going on, from what you're doing. I worked with automation equipment. So there was a lot of moving parts and a lot of different things going on. So we had to be really on top of guarding and the rules of guarding and the types of fasteners that you use to put guarding on and stuff like that. So we put it around everything, but I can't say for government stuff, it has to be on.
And every company and contract that you have will be different.
Good point, Deborah. Yes, every company and contract may be different because then they're also dealing with the liability of their workers and what they are, willing to risk for them. So you're right. So there might even be more stringent ones, but OSHA, got to use stuff like this. So that's why we end up seeing socket head cap screws, not only because you can tighten them down better and with more force when you have something like an Allen wrench, because you're getting more surfaces that you can actually, you have contact with to tighten it down, as opposed to like a slotted head. Okay. All right. So you want to be, especially when you're in those areas of safety and your products being, being operated by people who can get hurt by them, this is going to be something that you want front of mind and want to, make sure that you're following the rules, and especially whatever the company or the customer is looking for. So you'd want to stay away from stuff like this for guarding for sure. But even like I said, as we know, I mean, at home all the time, if you've got a slotted head screw, yeah, it's nice because you don't need a special, tool, but yet couple times that you torque them and take them on and off, all of a sudden they're all, like I said, they're all kind of messed up. So even Phillips ones especially, right? It's like, really? So anyway, so that's those are the different types. So heads wise, we've got a flat head. We've got round or button head, they're referred to as a lot. We've got a hex head, and that's about all you're going to see on this list. Okay, honestly. So if we look underneath my camera here, this is a socket head. Okay, so it's got the full, circle all the way around for a depth. And then this is what we would call a flat head. Now, yes, this has a slot on it, but they come with the caps, the hex heads, if you would. Okay, this just happens to be the one that I could find and I could steal from somewhere. So this is a flat head. Now, we will be designing, for instance, if you are accommodating the head of a bolt, it is going to then sit down into a counter bore. Okay. That counter bore is going to be large enough to put the bolt head in. Okay. And keep it down below the surface that we see here. A flat head, we are going to then put, the sides. This one doesn't necessarily fit in there, but that is going to be flush with the top of the piece. Okay. So in both cases, whether you use a, the flathead or the socket head, okay? In both cases, if you need to accommodate them going down below the surface, you would either do a counter bore or a counter sink, which is going to be the angles, okay? Now, if it's okay for it to sit on top, like we see here, that's totally fine too, okay? It just kind of depends. Is there something it's going to interfere with? Is it something that people could get caught on? That's really going to be the deciding factor, whether you do one or the other. Obviously, this is an extra little operation that has to be put in place. So if you don't need to counter bore something, you don't want to, okay? You want to just keep them on top. So it all kind of depends on the application. All right. Nuts. Okay, nuts are going to be used when you are interested in putting a bolt through and then securing it on the backside. And there's a lot of different ways that you can secure with nuts, and there's a lot of different types of nuts. So there's like a regular nut and a jam nut. A jam nut is going to allow you to lock it in place once it's there. Okay, that's going to be the short one here. You can have combination with different types of washers to kind of disperse the force of the nuts rather than digging in, if you would, to materials. We see it a lot with wood, right? Because you want to put that washer there so you have some surface that it can go out, but you can also use them in the case of metal applications. Here you're going to see a spring washer. That's where there's a little bit of a cut in there. I don't have an example of that in my little box here, but you're going to notice if I zoom in here, it kind of has a higher side and a lower side. And when you push this down, what that does is it puts tension on the washer, which then will help it to resist loosening up. So it's kind of a nice thing for that. And a lot of different, oopsie, I did the wrong thing here. What was I thinking? Hit the wrong button. Let me go back to my PowerPoint. Oops, wrong one again. I'm in a hurry, so I'm not reading. There we go. And now I got to go all the way down. Sorry. Let me get my chat box, minimize that for a second. I know we're towards the end here. There we go. Standard cap screws. Again, I differ for the book on this only because slots not going to be the choice that you're going to make for industrial design, and in our class too. If we're showing an assembly, for instance, and there was any slotted screws in there, we will always swap them out for socket heads. Okay. Machine screws are normally finished. Yeah. Cap screws. This is the difference between cap screws and then machine screws on the next. So a cap screw most often is going to have this little section where there are no threads. Okay. Machine screw is going to have threads all the way to the head. That's the difference. Okay. Machine screws also will go a little bit smaller in size. Cap screws will be a little bit bigger. So for instance, these go down to about a 1/16 of an inch diameter through 3/4 of an inch. And then these are going to start at higher values. Okay. So they're a little bit bigger. But I will say these are interchangeable, whether you use a machine screw or a cap screw. Honestly, it doesn't really matter. Strength of the threads is the same, all that kind of stuff, and the quality. The next ones here that we have are standard set screws. The only difference from set screws to regular cap screws is that they don't have a head on them. That's it. So these are going to be used most often for securing things that we don't want to turn. For instance, if we have like a collar on the end of a shaft and we have it secured, but we want to kind of give it a little bit extra insurance, a set screw is going to help us with that. So sometimes you'll also see in shafts where they don't want the key to move, they'll secure it with a set screw as well. Okay, so a lot of different places that we can use set screws, but it's a headless fastener, if you would. So you'll notice that in the inside here, this is that hex area. So we would use an Allen wrench, for instance, to loosen and tighten it up. And then we've got all different, lengths. And then there's a lot of different tips on the end as well. Some of them will be flat. Some of them will have a point. Some of them will have like little grippies to like actually get into a surface if they need to. So depending on the application. A key is going to be an element that we are going to incorporate when we want to transmit rotational speed and torque. Okay. We see keys in between shafts and, for instance, the hub of a gear, so that the hub of the gear has the key and it's going to be up a little bit. And then the gear will then rotate along with the shaft. It's also an element that we design to fail first. Okay. By design, we size them and we determine the material so that if there would be an overload of any sort, the key is going to fail first. A key is going to be either a Woodruff key like we see here, Oh, I thought there was another picture. Or it can be just a very easy rectangular piece of metal. A lot cheaper to replace and manufacture than a complex shaft, for instance, that has a lot of different things that are going on. Or a gear that could be very expensive and kind of hard to get, in immediately, where you can just cut a key and you're back in business. So that's what a key is. Pins and rivets. So pins and rivets are used to secure different elements so that they are not moving relative one to another. So a pin, a lot of times we're gonna see going through a collar, maybe even through a shaft in this case, and then they're going to secure on the back end. This is a taper pin. So a taper pin, we're gonna be basically tapping in, and it's gonna be wider at one end than the other, and it will naturally tighten up as it goes down through. Rivets are going to also be same thing. A rivet is going to take material. It's going to squish it together, if you would, and kind of secure things. We see rivets in a lot of different areas. Very cheap, easy ways to secure things. Used a lot in sheet metal applications. And then we have springs here at the very end. So springs is a huge subject. They just kind of show you this is what springs look like. They don't give you a whole lot. But in your machine design elements class, you will be doing a unit on sizing springs and looking at applications and such. So there's a lot to springs, and they even say there's a whole part of a standard that is used. So I'm not going to really go into springs at this time. And that's the very last section here. You're going to notice in the book it's very brief as well. So that kind of gets us through the concepts, if you would, for threaded features and fasteners as we have it in Module 6 here. So what I'm going to do is I'm going to stop our recording here, and then what we're going to do is we're going to look at the assignment that you have for Module 6, which is Module 6A is going to be our fastener assignment, and we'll be back with that.